All right, this video is about collision theory, which is the concept in chemistry that when a chemical reaction happens, molecules have to physically collide in order to make that occur. Driving questions that we are going to attempt to answer in this lesson are as follows. How does collision theory help us understand chemical reactions and their rates? 2. How does the Maxwell-Boltzmann distribution help us understand temperature and kinetic energy of particles? And 3. How do temperature and concentration impact rates of reaction in terms of collision theory? So we're going to kind of go through these one by one and see how we can apply collision theory and learn from these various models and explain temperature and concentration. All right, so what is collision theory? Well, as it states here, collision theory is the idea that reactions require collisions to occur between reactant molecules. So what we have to appreciate is that every time potential reactant molecules collide, they're not necessarily what we would call successful collisions, okay? There can be collisions between reactant molecules that do not result in a reaction, and that would be an unsuccessful collision. So a successful collision, as it says here, is one that results in a chemical reaction occurring or a product being produced. So for example, if we look at the green molecule here and the blue molecule here in this little scenario to the left, we're saying that they have to collide in order for a reaction to happen. And even if they collide, it may go ahead and produce a product, or it might not produce a product, and they just might go back to their original reactants. So let's look at what can help determine that. Okay, so for a collision to be successful, how does a collision actually end up being what we would deem a successful collision, meaning one that will result in a chemical reaction? Well, first of all, the first thing that has to be correct is particles must have sufficient collision energy. So they must have what we often call the minimum collision energy necessary. They have to be moving fast enough, is what it kind of means in everyday speak. Their kinetic energy needs to be higher than what we call the activation energy for that specific reaction. And so the minimum kinetic energy required is kinetic energy or speed of particles hitting each other, which is greater than or equal to the activation energy for that specific reaction. So for example, if you look at the green molecule there and the red molecule, when they're flying together and they're going to smash into each other and collide, they have to be moving with enough speed, essentially. And we should appreciate that each reaction has its own specific activation energy based on the nature of the reactants. So it's going to be different for every different reaction. The second criteria which must be met for a collision to be successful is that particles must collide with acceptable collision geometry, as we say. And that basically means that they have to collide at the correct angle. Okay, this is all about the angle at which they hit one another. It has to be right. So let's break that down a little bit more, this collision geometry aspect here. So if we basically examine the geometry of a collision, meaning we look at the angle with which particles are colliding, there's going to be an acceptable range in that angle, and there's going to be basically some ways that molecules are going to hit that is not going to result in a successful collision. So particles have to collide at the correct angle so that the bonds in the reactants will break and the new bonds in the products will form. So hopefully this is something that you realize has to happen in every chemical reaction. And if you didn't, well, you're hearing it now. In every chemical reaction, the bonds of the reactants need to break apart and the bonds of the products need to form. Okay, so if they don't hit at the right angle, it's not going to happen. So if you look at, for example, the reaction in question here, the NO2 plus carbon monoxide making CO2 plus nitrogen monoxide, we're just going to examine the reactants, so just the NO2 and the carbon monoxide. And so, for example, in scenario 1 here, which I'll just go ahead and label that. That's in scenario 1. We see that they have those long blue arrows, and I'm trying to suggest there that they're moving fast. So they have good speed, and good adequate kinetic energy, and they're also hitting at an angle, which I'm just arbitrarily making up for the sake of example, but I'm saying that this is the correct angle that they need to hit at, so we could have a successful collision there. If you look at scenario 2, they are no longer hitting at that same angle, right? Now you see that this one, that the carbon monoxide is hitting at a 90-degree angle to what it was before, according to this picture. And so they might still have good speed. In other words, the blue arrows I drew are still really long, and presumably they were flying at each other fast. But now they have the wrong angle, and so it's likely this is going to be an ineffective collision. It's not going to result in a chemical reaction. And then the third scenario, you can see the angle is correct, but now the little speed arrows have gotten smaller. And so I'm trying to indicate this is too slow. And so whether or not it actually had the correct geometry or not, it's too slow even though the angle was right, and so it's not going to result in an effective collision. So the two factors are the speed and the geometry, or the kinetic energy and the geometry. So understanding that really reactions are all about collisions, we can then take a deeper dive into explaining some of the factors which we know can increase rate of reaction, and one of them is concentration. We know that if we increase the concentration of the reactants, that the rate of reaction increases. But why is that? Well, now with collision theory, we can explain that. It's because if we have an increased concentration of reactants, there's going to be more frequent particle collisions between the reactants. And so when you have more particles in the same unit volume, they're going to hit each other more frequently, and so therefore there's also a greater likelihood of successful collisions. In other words, like when you have a net gain in the number of collisions, there's a greater likelihood that some of those collisions will be of adequate kinetic energy and hitting at an adequate angle to make a successful collision. The other factor that we can now better explain in terms of collision theory is temperature's effect on rate. So we already know that when temperature increases, the rate of reaction increases. Okay, but why is that? Well, applying collision theory, we can actually explain that there's two reasons behind this, or really two kind of methods of efficacy for the temperature effect. One is that it's going to result in more frequent collisions between molecules. So if you have a sample of reactant molecules in a vessel and you increase the temperature, on average you are increasing how fast they're all moving around. And if they're moving around faster, they're going to run into one another more frequently. So that's going to make a greater likelihood then of having successful collisions because there's more frequent collisions. The second factor is that of those collisions happening, a greater proportion of the collisions will happen at a higher kinetic energy. So a greater proportion of them will have the minimum kinetic energy required to react. In other words, a greater proportion of them will have a kinetic energy greater than or equal to the activation energy. If you want to try and quantify this a little bit more specifically, and we'll get into these details as we look at the Maxwell-Boltzmann distribution, but for every 10-degree increase in temperature, the general rule is that the rate of reaction will double. So every time you increase it by 10 degrees Celsius, the rate of reaction will get twice as fast. So if you're increasing it by, let's say, 20 degrees Celsius, you would expect it to get 4 times faster. And so in line with the concept of how temperature increases rate according to increasing the number of collisions and increasing the proportion of collisions that happen at high energy, we have the Maxwell-Boltzmann distribution, or the Maxwell-Boltzmann curve. I would encourage you just to pause the video for a second and see if you can explain what the Maxwell-Boltzmann curve shows you. What it actually shows in the Maxwell-Boltzmann curve is that if we have a sample of matter, so let's say we actually have just imagine a beaker full of some sort of fluid that is going to react, okay? So if we have it in here, what it's trying to say is that every molecule in that sample is not moving at the same speed, okay? Just like you might, practically expect with all sorts of other things, every single molecule is not the same. The speed of the particles we consider, the kinetic energy of the particles, we really consider the average when we're measuring it. And that's what we would refer to as the temperature. So remember that temperature is your average kinetic energy of the sample. And what's actually being shown on the Maxwell-Boltzmann distribution, the Maxwell-Boltzmann curve, is it is like a statistical curve, kind of like a bell curve or a Pareto distribution. And so what it's trying to show is that most molecules in a sample will have a kinetic energy somewhere between here and here. So by and large, most of the molecules in a sample have this average kinetic energy. But there will be some molecules in that sample that have a very high kinetic energy, and they're at the right tail here. And there'll be some that are moving very slowly and have a very low kinetic energy, okay? But on average, if you want to know the temperature, you're going to drop a vertical from the highest point of the curve, okay, from like right here, and then you're going to drop that down, and whatever the kinetic energy is here is going to be what we would call the temperature because it's the average kinetic energy. Well, what's the significance of this, of looking at the kinetic energy of all the particles in a sample? The significance is that we're only going to expect those of the highest energy to be reacting at any given moment in time if the reaction, as we know it is based on how fast the particles are moving. Because there's going to be a certain cutoff point, which we call the activation energy, which is going to actually control what particles have enough energy to react. So if we take a look at this second drawing of the Maxwell-Boltzmann distribution that I made here, I've added a couple of features. So one thing I've added is I've put in a line representing the activation energy, and that's this black line right here, okay? So this black line is actually representing like the cutoff point. Any molecules to the right of that line would have kinetic energy high enough to, large enough to react, okay? Any molecules to the left of the line do not have a kinetic energy large enough to react when they collide, okay? So as you can see, what I've tried to represent here is that the Maxwell-Boltzmann distribution for, the same sample, so I'm trying to emphasize that the area under each curve would be the same, curve T at temperature 1, curve at temperature 2, and curve at temperature 3. The area under each one is the same. But what would happen, or how would the Maxwell-Boltzmann distribution change if we change the temperature? So temperature 1 is lower than temperature 2, which is lower than temperature 3. Well, what happens is you can see temperature 1 is the coldest, okay? And so its average, if you look at where the peak of that curve is, its average is going to be here. Okay, so its temperature is the coldest. Remember, temperature is average kinetic energy. You can also see that it has the smallest proportion of its molecules beyond the activation energy. If we then compare that to the second curve that got a little bit warmer, temperature 2, we can see that now temperature 2 has a greater proportion of the molecules with enough kinetic energy to react upon collision. And what we can also see is that the average, the top of the curve, if we drop that down, the average kinetic energy is higher, so the temperature has increased. The other thing that is important is we see that the peak has shifted over, right? And it's flattened out a little bit. It shifts over because the average kinetic energy is greater, and it flattens out because the area under each curve needs to be the same in order to, be making a fair test and saying this is the same sample of matter. If we then move to the warmest scenario, okay, temperature 3, we can see that now the greatest proportion of all, a larger proportion of its molecules have kinetic energy beyond the activation energy, and so we expect this reaction to happen faster, like we expect with warmer reactions. And we can also see that the average kinetic energy has shifted right over here, and so this would be the highest temperature of all 3 samples. Again, don't forget that general rule. I hate to maybe use the term rule, but it's a general idea, kind of an assumption we can make, the 10-degree rule. For every 10 degrees Celsius, the rate of reaction will double, so you can see it doubles if we go from 10 to 20, and it actually quadruples if we go from 10 to 30 degrees. We looked at a Maxwell-Boltzmann distribution with one temperature on it. We looked at one where we compare the same sample of matter at different temperatures. Now let's look at one for different reactions altogether, looking at two different, Maxwell-Boltzmann distributions for two separate reactions. So we have reaction 1 right here, which might be, I'm just making this up, like, molecule A reacting into molecule B. And then we have reaction 2 right here, which would be like molecule C reacting into molecule D. And what you can see is that the activation energy barrier for the second reaction is actually backed up, isn't it? So you can see the activation energy barrier is actually lower for reaction 2, which means at any given temperature, in this case 20 degrees, reaction 2 would proceed faster than reaction 1 because a greater proportion of its molecules have a kinetic energy sufficient to overcome the activation energy barrier or meet the minimum kinetic energy requirement for a reaction. Just one thing to not get jammed up on here as we continue to talk about heat and activation energy and potential energy is don't confuse how much heat or energy can be released by a reaction with the activation energy for that reaction. For example, we know that dynamite or other fuels are highly flammable, but they also need a match or an initial spark or an initial input, great input of heat in order to provide enough energy to get them to overcome their activation energy barrier. So although a lot of fuels have a lot of energy that can be released in them and they're very exothermic reactions, they can have a very high activation energy, and that's why we need to light them on fire to get those reactions started.